So we're going to start part 2 of the heart. We last time in the last 2 videos discussed some general concepts of the heart and what they wanted us to know about the electrical system of the heart. Now the next section in the book kind of includes a couple of the concepts that we have talked about already. The cardiac mechanical activities are listed here. We're going to start talking about more of the parameters of cardiac function in this section. So we've already established that the muscle contraction is due to an electrical activation, the atria before the ventricles. The ventricles eject the stroke volume, both into the aorta and the pulmonary system. Our stroke volume equals our end diastolic volume minus the end systolic volume. And I hope that that is something that makes sense to you guys as we move through. We'll talk more about that. That really helps us understand that better. Remember, we talked about the heart being a single organ with 2 pumps. The cardiac muscle contains, which we talked about, the actin and the myosin lined up with the sarcomeres. We have the entry of the calcium during our action potential phase 2 to provide the calcium needed to bind to troponin C. Binding of calcium to troponin shifts tropomyosin, exposing actin binding sites to the myosin heads. The myosin heads bind and swivel, moving the strands relative to one another. Mechanically coupled cells contract almost simultaneously, and the contraction leads to the squeezing of the chambers, which leads to emptying of the chambers. This is the steps in the myosin actin cross bridge formation that's in your book. What we need to know on this slide is what we did already talk about in osmosis, is that it requires calcium and ATP together. The sliding filaments of the sarcomere create the muscle contraction as they slide and go to move and contract the heart. Again, I think osmosis did a fabulous job of explaining that. I'm not going to spend a lot of time. This is now the part where the book goes into the T-tubule to show us that it's adjacent to the sarcoplasmic reticulum terminal cistern. The action potential proceeds down the T-tubule and then the calcium entry through the dihydropyridine receptor, which activates the SR calcium release via the ryanodine receptor. The calcium spreads through the cytoplasm, binding to troponin C on actin, and we get this cross-bridge formation. This was explained again in our osmosis videos that we watched up until this point of the cross-coupling contraction in the heart cells. I'm going to let us watch it then one more time to really lay it in and hit home for us. Here we go.
When a depolarization wavefront hits a cardiomyocyte, a few calcium ions flow through gap junctions. And if a threshold membrane potential is reached, then sodium channels start to open up. If there's a depolarization, then ions start to move across the cell membrane, and that's where the T-tubules play a key role. During the part of the cardiomyocyte action potential when calcium ions flow into the cell, the presence of T-tubules helps bring calcium deep into the cell. Once this extracellular calcium gets inside, it binds to the ryanodine receptors on the sarcoplasmic reticulum, which releases even more calcium into the cell, a process called calcium-induced calcium release. The calcium helps activate 2 contractile proteins, actin and myosin, which are called myofilaments, and are ultimately responsible for cell contraction. And that's the key moment when the chemical signal is converted into a mechanical signal. When calcium ions enter the cardiomyocyte, they bind to troponin C, which is attached to a long thin protein called tropomyosin. Tropomyosin is draped around yet another protein filament called actin, where it covers up binding sites, so that the actin can't be bound by myosin heads which are lurking nearby. This is kind of like a protective parent that doesn't want their child to go out on a date. Those calcium ions bind to troponin C, and that causes tropomyosin to slide off of the actin filament, exposing the actin binding sites. At that point, myosin heads bind to actin, and this forms a cross bridge. When the parent's away, the children will play. The myosin head pushes past the actin with a power stroke, effectively pulling the actin and myosin filaments past one another and shortening the muscle. The myosin does this a few times with actin, binding, sliding past, reattaching, and then repeating this process and using up ATP along the way. The myosin head looks kind of like an oar in a boat. It hits the water, shifts, then comes out, and this only works in the presence of calcium ions. Eventually, calcium ions are removed by ion transporters that rely on ATP or concentration gradients. Most of the calcium gets moved back into the sarcoplasmic reticulum, or the extracellular environment, and some also moves into the mitochondria. Once that calcium is gone, the troponin goes back to its original shape, which blocks the binding sites on the actin and prevents more cross bridges from forming. Alright, as a quick recap. Cardiac excitation-contraction coupling is when an action potential is converted into mechanical energy. Calcium ions move into the cell via T-tubules and bind to troponin. The troponin changes conformation and exposes more of the actin filament, which has binding sites for myosin. Myosin-actin bridges form using ATP and are part of the power stroke that pulls actin and myosin close together, forming the basis for muscle contraction.
Which I think they explain it very well. Next, we move on to talking about the sympathetic nervous system and how it increases contractility. We already spoke earlier about how it increases the heart rate when norepinephrine and epinephrine work on the beta-1 adrenergic receptors, and we move that potential forward, and it causes an increase in the heart rate. Now we're going to talk about how the sympathetic nervous system increases contractility. We have sympathetic nervous system fibers extensively throughout the ventricles, which is an image that is in your book that we don't have on the slide. It's figure 10.23. The sympathetic transmitter norepinephrine then is the one that's going to change our cardiac performance the most. During our physiological challenges, such as exercise or being chased by a bear, fight or flight, we have sympathetic activity then that's going to increase the heart rate and improve the contractility. When you improve the contractility, what are we doing? We're increasing our cardiac output to be able to meet the sudden demand of the tissues. So we need to have our contractility increase as well. So we can see here that the norepinephrine binds to the beta-1 receptors on the ventricular myocardial cells, which then works with the GS protein here and adenyl cyclase. So we're going to increase our intracellular CAMP, followed by activation then of what we spoke of before, the pKa. The pKa phosphorylation phosphorylates the membrane calcium channel and phospholambin here. The consequences are that the increased calcium influx, stimulating the calcium-initiated calcium release out of the sarcoplasmic reticulum, means greater cytoplasmic calcium elevations, promoting a stronger contraction. Greater amounts of the calcium stored in our sarcoplasmic reticulum is released, increasing the strength of the subsequent contractions and the faster rate of relaxation in diastole. So it's this set of changes that contributes to the increased stroke volume, which increases our cardiac output. It's a faster system to help increase the productivity, right? All right, so when we're talking about the stroke volume, so we're beginning to talk about the parameters of hemodynamics and cardiac output and all of these terms that maybe you guys are very familiar with if you've worked in a lot of ICU settings. But we are going to start breaking down the hemodynamics and all the different cardiac parameters that affect cardiac output. So remember when we say stroke volume, essentially we're talking about what? It's the amount of volume ejected from the left ventricle during systole. And so that volume, that the amount of blood that's going to be able to get into the arterial system is going to have a couple of different factors that will decide how much of the volume is going to go out. Okay. So one, we have preload, which is the degree of ventricular filling. So at the end of diastole, the volume that we have then, so at the end of the ventricles at rest, when the water balloon has stretched as full as it's going to, that is our preload. So that is the volume coming into a ventricle to stretch it like the water balloon. So at the very end, right before it's going to begin contraction, at the end of diastole, that is our volume. So that's the volume we have to work with. That is the volume, the bucket, the balloon full of the blood that we're going to eject during the contraction. So if I want to eject the amount of blood that's going to come out with my systole, I need to fill up the water balloon more, which is increasing our preload. So if we increase the volume that is allowed to come into the ventricle, then I'm going to be able to also, ergo, have increased volume getting squeezed out of the ventricle. Okay, so if I want to talk about how I can influence my stroke volume, I can manipulate my preload. If I increase my preload, I'm going to have more volume in my stroke volume. If I decrease my preload, I'm going to decrease my stroke volume. Same thing that's going to affect that amount that's able to get ejected during systole is going to be how much pressure I need for afterload. So now we're talking about the pressure that the heart must generate to open the aortic valve and get the blood out. So how hard does my heart have to work to get that blood to come out? And now this means that the increase in afterload is going to decrease the amount of volume I can actually get out. So the harder the heart has to work to get blood out, the less it's going to do. And so inversely, if I decrease afterload, so I decrease the pressure that the ventricle has to make, then the ventricle is able to squeeze out more. So I can inversely manipulate my afterload to change my stroke volume. So preload and afterload, if I go down in preload, I go down in stroke volume. If I go up in preload, I go up in stroke volume. But afterload is inverse. So if I go increase my afterload, I'm going to decrease my stroke volume. If I decrease my my afterload, I will increase my stroke volume. Then the other thing that's going to affect my stroke volume is going to be my contractility. So the ability then of that muscle to generate that force primarily depends on the sympathetic nervous system stimulation and how norepinephrine action is working on that beta-1 adrenergic receptor site. So these are some of the factors that we are going to begin to have to understand when we're talking about this. Okay, so we're talking about preload influences stroke volume. This is the part one, and this is Frank Starling's law of the heart. So, let's get into that.
More than a century ago, two physiologists, Otto Frank and Ernest Starling, discovered that as the heart gets filled up with more blood during diastole, it contracts harder and pumps out more blood during systole. Naturally, they came up with the Frank-Starling law to explain this relationship. To understand the relationship, let's zoom into the walls of the ventricles. The bulk of these walls is made up of short, branched cardiac muscle cells packed one next to the other. Zooming in further, if we look inside the muscle cells, we see bundles of myofibrils, or long chains of sarcomeres. The sarcomere is the smallest structure in the muscle that's capable of contracting, so it's considered the basic contractile unit of the muscle. The sarcomere has two Z discs that form its boundary, and an M line in the middle. Attached to the Z disc are thin filaments made of actin protein. These actin filaments have structural polarity, which means both ends of the filament look different. We can think of it like an arrow, with the pointed end being the minus end, pointing towards the M line, and the tail end being the plus end, attached to the Z disc. Just like an arrow, the actin filament can only move in one direction, the direction it's pointed at. Attached to the M line are the myosin filaments, which are thick bundles of myosin proteins with two globular heads. During a muscle contraction, the myosin heads grab onto the actin filaments and pull them towards the M line, which brings the two Z discs closer together. Overall, the amount of tension developed, or the force of muscle contraction during systole, depends on the number of myosin heads that bind to actin. And this number directly depends on the length of the overlapping section between actin and myosin filaments. The length of the overlapping section depends on the overall length of the sarcomere. And the length of the sarcomere depends on how much blood fills the ventricle during diastole, because that affects how stretched out the overall muscle wall and each sarcomere within it end up being. This relationship is known as the cardiac length-tension relationship, and it can be shown by this graph, with the sarcomere length or the ventricular end-diastolic volume on the x-axis, and the tension or pressure developed within the ventricle during their contraction or systole on the y-axis. So let's imagine that the ventricles are mostly empty, with almost no blood in them. This would mean that there's nothing stretching the muscles in the ventricular wall, so the length of the sarcomeres are really short. At this length, the two Z discs are pulled close to each other and there's not much room for further contraction. Furthermore, the actin filaments from each side of the sarcomere cross the M line and overlap. Since actin can be pulled only in one direction, towards the midline, myosin has to attach and pull the actin filament with the right structural polarity, the one pointing in the same direction as the myosin pulls. So when the actin filaments overlap, myosin is prevented from binding to its own actin filament by the actin filament from the other side with the wrong polarity. As a result, very few myosin-actin attachments are made and the cells can contract only very weakly during systole. On the graph, we can see near the point of origin, the short length of myocardial fibers corresponds with a low contractile force. As the ventricles fill with more blood returning through the veins, their walls get more and more stretched, and that stretches out every single sarcomere in the muscle cells as well. This means that there's more space, and no actin overlapping, which allows more myosin heads to properly interact with actin, and as a result create more force, or tension, during contraction. Looking at the graph, this would make our curve move steadily upwards with increasing force as there's increasing volume. This stretching can go until it exceeds a maximal point, after which things start getting too stretched out. This means the Z discs are so far apart from each other that there's only little overlap between actin and myosin filaments, and actin gets out of reach from the myosin. As a result, there's a decreased number of myosin heads that manage to attach to actin and pull it towards the M line. This leads to a decreased force of contraction, so the curve starts falling off again. Now that we've seen the relationship between length of the sarcomeres and tension during contraction and systole, let's look at the Frank-Starling relationship. This can also be plotted onto a similar graph, with the ventricular end-diastolic volume on the x-axis, and the stroke volume, which is the volume of blood pumped out by the ventricle with each heartbeat, on the y-axis. So at the start of the curve, near the bottom left-hand corner, we have a low end-diastolic volume, meaning very little blood in the ventricle at the end of diastole. So sarcomeres are squeezed together with very few myosin heads binding to actin. This results in a weak contraction during systole and a low stroke volume. As the volume of blood returning to the ventricles increases, sarcomeres stretch, and there's more myosin-actin binding, so a greater strength of contraction is achieved and stroke volume rises. That's true until the end-diastolic volume becomes too high, and the myosin and actin get too far apart, which causes the amount of myosin and actin binding to decrease, which results in a weaker contraction, so the stroke volume falls off again. Keep in mind, though, that this curve reflects the heart's intrinsic ability to vary the strength of contraction based on the volume of blood that it's filled with. Within the body, there are plenty of extrinsic signals as well, like nerve or hormonal stimuli and medications. Some of these signals, like stimulation from the sympathetic nervous system or the medication digoxin, can have a positive inotropic effect on the heart. This means that at a given end-diastolic volume, they increase the strength of contraction, moving the curve upwards and increasing the stroke volume. On the other hand, there are negative inotropic agents, like medications, like beta blockers, that decrease the strength of contraction, moving the curve downwards and decreasing stroke volume. Alright, as a quick recap, the Frank-Starling relationship between end-diastolic volume, contraction strength, and stroke volume states that the strength of ventricular contraction and the volume of blood ejected by the ventricle depends on the blood volume present in the ventricle at the end of diastole.
Thank you, osmosis. So the greater filling of the ventricle stretches the sarcomeres, promoting the optimal length for force of contraction. So the second factor that we talked about is that preload influences our stroke volume, right? So the greater filling the preload produces greater stroke volume. This relationship is modulated by contractility. So increased contractility improves stroke volume at any preload. Decreased contractility reduces stroke volume at any preload. So if I increase, let's say this all together. If I increase my preload, I will increase my stroke volume. But if I increase my contractility, I'm also going to increase my stroke volume at any preload. So it's kind of saying the same thing in a weird way, as you can see here in these on this slide here. What this is showing us is that increased contractility that could result from our sympathetic stimulation shifts the curve upward, so the purple becomes the green, increasing the stroke volume at each level. But if you have a weakened muscle associated with like heart failure, you're not going to achieve adequate stroke volume to sustain physical activity at any level of preload, is what we're trying to say there. So at some point, yes, preload and stroke volume influence each other, but also at the end of the day, it depends on the relationship, or the relationship depends then on the contractility of the heart. What your book also talks about that I wanted to point out is that it says physiologically, increased preload occurs during exercise because muscle activity squeezes the veins, increasing the volume of venous return to the vena cava and to the heart. So one of the mechanisms our body does when we start to exercise and we need more cardiac output. So I need to increase my stroke volume. I need to increase my preload. Then it activates the muscles that we're using in the venous system, and that starts actively pumping the venous pool reserve that we talked about up now through the inferior vena cava back into the atria, and we have increased our preload. This mechanism provides the component of the enhanced stroke volume and cardiac output needed to support our sudden demand of increased oxygen consumption. Trained athletes will develop chronic improvements in cardiac function with increased left ventricular filling and contractile performance. So as a really well-trained athletic person, one indication that you are in incredibly good shape as an athlete is that you will have a slower resting heart rate because you have improved your baseline left ventricular filling and output. So when you're not exercising, your heart can be at a slower rate to maintain cardiac output because you have such a high stroke volume. So I did want to put that out. I did want to point out again what they're saying is that the positive inotropic, when we are talking here, the positive inotropic effect of the sympathetic stimulation is seen at any preload. An increased sympathetic activity shifts the preload and contraction strength curve in an upward direction. So the result is you do get greater contractile strength and stroke volume at any level of preload. I hope that's all making sense to everybody. To go back to what we were talking about here, the afterload. So let's talk about that again in a little more detail. We're going to jump in here real quick, actually, and add in the osmosis video about preload.
Cardiac preload is one of the main factors that influence how much blood the heart pumps out with each heartbeat or stroke. Now remember that the heart has two upper chambers. The left atrium, which receives oxygenated blood from the lungs via the pulmonary veins, and the right atrium, which receives deoxygenated blood from all of our organs and tissues via the superior and inferior vena cava. From the atria, the blood flows into the lower chambers of the heart, the left ventricle, which pumps oxygenated blood to all our organs and tissues via the aorta, and the right ventricle, which pumps the deoxygenated blood back to the lungs via the pulmonary arteries. Alright, now each heartbeat consists of two phases. Systole, which is when the heart contracts and pumps the blood out of the ventricles, and diastole, which is when the heart relaxes and ventricles fill with blood. And as the left ventricle fills with blood during diastole, the pressure within it rises. The pressure at the end of diastole is called the left ventricular end diastolic pressure, which is a key determinant of cardiac preload. So cardiac preload can be defined as the ventricular wall stress at the end of diastole. And it can be calculated using the law of Laplace, which states that wall stress equals pressure P times radius R over 2 times wall thickness W. Another way to say this is that cardiac preload is directly proportional to the end diastolic pressure and radius of the left ventricle, and indirectly proportional to 2 times the ventricular wall thickness. To visualize this, let's look at a cross-section of the left ventricle, which looks a bit like a donut, with little dough. A diet donut, if you will. Now the little dough circle represents the wall of the left ventricle, and its thickness is the ventricular wall thickness, or W. Pressure, or P, on the other hand, is determined by the volume of blood inside the ventricle at the end of diastole. And finally, the radius is the distance from the center of the ventricle to the outer edge. So actually, the radius, or R, comprises of an inner radius, or RIN, which is the radius of the ventricular cavity. And the full radius is RIN plus the ventricular wall thickness. And if you thought we were done with math, hold your horses, there's one more formula we need to calculate. The inner radius, which is RIN, equals the cube root of 3 times V over 4 times pi, where V is the volume of the left ventricle at the end of diastole. Or RIN equals 3 times V over 4 times pi to the power of 1 over 3. And then we can add wall thickness to the inner radius to determine the left ventricular end diastolic radius, or R. Alternatively, preload can be defined as the length of muscle fibers, or sarcomeres, at the end of diastole. So let's zoom in on the wall of the left ventricle. The bulk of these walls is made up of short, branched cardiac muscle cells packed one next to the other. Zooming in further, if we look inside the muscle cells, we see bundles of myofibrils, or long chains of sarcomeres. The sarcomere is the smallest structure in the muscle that is capable of contracting, so it's considered the basic contractile unit of the muscle. Zooming in further, you can see that the sarcomere has 2 Z-discs that form its boundary, and an M-line in the middle. Attached to the Z-disc are thin filaments made of actin protein. These actin filaments have structural polarity, which means the end of the filament look different from one another. We can think of it like an arrow, with the pointed end being the minus end, pointing towards the M-line, and the tail end being the plus end, attached to the Z-disc. Just like an arrow, the actin filament can only move in one direction, the direction it's pointed at. Attached to the M-line are the myosin filaments, which are thick bundles of myosin proteins with 2 globular heads. During a muscle contraction, the myosin heads grab onto the actin filaments and pull them towards the M-line, which brings the 2 Z-discs closer together. So the length of the sarcomere is important because the force of contraction during systole depends on the number of myosin heads that bind to actin. This number directly depends on the length of the overlapping section between actin and myosin filaments. And the length of the overlapping section depends on the overall length of the sarcomere. But no matter how we choose to define cardiac preload, the problem is that these measurements are not possible in practice. Imagine trying to measure the length of sarcomeres in vivo. Therefore, in clinical practice, a surrogate for cardiac preload is used. Specifically, the volume of blood within the left ventricle at the end of diastole that stretches out the overall muscle wall and each sarcomere within it. It's important to note that the end diastolic left ventricular volume is not the same as cardiac preload, but it can be measured with an echocardiogram, so it's easier to use this parameter in practice. Now, the left ventricular end diastolic volume, and therefore preload, is affected by 5 factors: venous pressure and rate of venous return, atrial contraction, resistance from valves, ventricular compliance, and heart rate. First, let's focus on venous pressure and the rate of venous return. Venous pressure and the rate of venous return are influenced by 2 other factors, venous tone and circulating blood volume. Now, venous tone is determined by vasodilating and vasoconstricting factors. Vasodilating factors relax smooth muscle cells within the vein walls, thereby decreasing the vascular tone of the vein. One such vasodilating factor is atrial natriuretic peptide, or ANP, which is secreted by cardiac muscle cells in the walls of the atria in response to an increased circulating blood volume that makes an increased amount of blood reach and distend the atrium. When ANP is secreted and venous tone decreases, that results in peripheral pooling of the blood and decreased return of the venous blood to the heart. Moreover, the decreased return of the venous blood leads to decreased left ventricular pressure and decreased end diastolic volume, and therefore decreased cardiac preload. Another way to visualize this is through pressure-volume loops, which are graphs that show the pressure inside the left ventricle on the y-axis and the volume of blood inside the left ventricle on the x-axis. And the green dotted loop represents the variation over the course of one cardiac cycle under normal circumstances. When vasodilating factors are secreted and cardiac preload is decreased, left ventricular pressure and end-diastolic left ventricular volume both decrease. So the loop shifts to the left. On the other hand, vasoconstricting factors, such as sympathetic stimulation during the fight or flight response, constrict smooth muscle cells within the vessel walls, thereby increasing the vascular tone of the veins. This results in an increased venous return to the heart. Eventually, this leads to an increased end-diastolic volume and therefore increased cardiac preload, which helps send more oxygenated blood to organs and tissues. This might come in handy if a pack of kangaroos started chasing you at the mall. And if we look back at our pressure-volume loops, increased left ventricular pressure and end-diastolic volume, and the resulting increased cardiac preload, shifts the loop to the right. Speaking of which, the amount of circulating blood volume also influences venous pressure and venous return rate. Now, an average adult has a circulating blood volume of 5 liters. Next factor is atrial contraction. Increased force of atrial contraction, either by sympathetic stimulation of the heart or increased filling of the atria, increases the volume of blood that enters the ventricle, eventually causing an increase in end-diastolic volume, or EDV, and preload. On the other hand, when the atria can't pump blood efficiently and in sync, which is common in atrial arrhythmias, the volume of blood that enters the ventricle will decrease, eventually causing a decrease in end-diastolic volume and preload. Okay, next up, there's resistance from valves. This refers to the inflow valves that connect the atria and the ventricles, such as the mitral valve on the left and the tricuspid valve on the right, and the outflow valves which connect the left and right ventricle to the aorta and the pulmonary artery, respectively. Inflow resistance is created by the narrowing of atrioventricular valve openings such as mitral stenosis and tricuspid stenosis. This results in decreased filling of the ventricles and therefore decreased preload. Next factor is ventricular compliance, which is, simply said, the flexibility of the ventricles. Compliant, stretchy ventricles, such as seen in dilated cardiomyopathy, increase preload, while non-compliant stiff ventricles, such as seen in ventricular hypertrophy, decrease preload. And finally, there's heart rate. Normal heart rate, 60 to 100 beats per minute, allows adequate time for ventricles to fill, while abnormal heart rates, such as fast heart rhythm or tachycardia, reduce the filling time, eventually decreasing preload. Alright, as a quick recap, preload is defined as the ventricular wall stress at the end of diastole. Through the law of Laplace, we can say that wall stress is directly proportional to the ventricular end-diastolic pressure and radius, and indirectly proportional to 2 times the ventricular wall thickness. Alternatively, preload can be defined as the length of muscle fibers or sarcomeres at the end of diastole. But since these definitions are more theoretical, in clinical practice, the end-diastolic volume is used to assess cardiac preload. Finally, the end-diastolic volume and therefore preload is affected by 5 factors: venous pressure and rate of venous return, atrial contraction, resistance from valves, ventricular compliance, and heart rate.
Good job. And I'm going to also throw in the cardiac afterload video as well. Sneak this in here for us.
Cardiac afterload is one of the main factors that influence how much blood the heart pumps out with each heartbeat or stroke. Now remember that the heart has 2 upper chambers: the left atrium, which receives oxygenated blood from the lungs via the pulmonary veins, and the right atrium, which receives deoxygenated blood from all of our organs and tissues via the superior and inferior vena cava. From the atria, the blood flows into the lower chambers of the heart, the left ventricle, which pumps oxygenated blood to all our organs and tissues via the aorta, and the right ventricle, which pumps the deoxygenated blood back to the lungs via the pulmonary arteries. Alright, now each heartbeat consists of 2 phases: systole, which is when the heart contracts and pumps the blood out of the ventricles, and diastole, which is when the heart relaxes and ventricles fill with blood. And as the left ventricle fills with blood during diastole, the pressure within it rises. Then, the left ventricle contracts, increasing the pressure within the left ventricle even more and forcing blood through the aortic valve into the aorta and whole arterial system. So cardiac afterload can be defined as the ventricular wall stress during systole or ejection. And it can be calculated using the law of Laplace, which states that wall stress equals pressure P times radius R over 2 times wall thickness W. Another way to say this is that cardiac afterload is directly proportional to the pressure inside the left ventricle during ejection, as well as the radius of the left ventricle, and indirectly proportional to 2 times the ventricular wall thickness. To visualize this, let's look at a cross-section of the left ventricle, which looks a bit like a donut with little dough, a diet donut,
a little
if you will.
bit there.
Now the
here.
And if you thought we were done with math, hold your horses. There's one more formula we need to calculate, the inner radius, which is RIN equals. So left ventricular afterload is affected by systemic vasculating 2 variables, radius and wall thickness, during ejection. And if we assume that left ventricular pressure during ejection is equal to aortic, so left ventricular afterload is affected by systemic vascular resistance, as well as aortic pressure and valve diseases. Systemic vascular resistance is the resistance of systemic blood vessels to blood flow. In other words, how readily blood vessels allow blood to flow through them. Now, systemic vascular resistance is mainly affected by changes in the vessel lumen, which is determined by vasodilating and vasoconstricting factors. Vasodilating factors such as atrial natriuretic peptide, or ANP, which is secreted by cardiac muscle cells in the walls of the atria in response to an increased blood volume, relax smooth muscle cells within the vessel walls, thereby widening the vessel lumen. This results in decreased systemic vascular resistance and therefore decreased afterload. On the other hand, vasoconstricting factors, such as sympathetic stimulation, constrict smooth muscle cells within the vessel walls, thereby narrowing the vessel lumen. Eventually, this leads to an increase in systemic vascular resistance and therefore increased afterload. And finally, let's look at valve diseases. First, next one is aortic pressure. Increased aortic pressure means that the heart must contract harder and generate more pressure within the left ventricle in order to overcome aortic pressure and open the aortic valve. Therefore, increased aortic pressure increases afterload, while decreased aortic pressure reduces afterload. And finally, let's look at valve diseases. First, let's start with the aortic valve, which is between the left ventricle and the aorta. If the aortic valve doesn't open all the way, which is called aortic stenosis, the heart must generate more pressure in order to eject blood during systole. This increases the stress on the left ventricular wall, therefore increasing afterload. On the flip side, there's mitral regurgitation, which is when the mitral valve, which is between the left atrium and the left ventricle, doesn't close all the way. So during ejection, blood leaks back into the left atrium. This decreases the stress on the left ventricular wall, therefore decreasing afterload. Alright, as a quick recap, afterload is defined as the left ventricular wall stress during systole or ejection. Through the law of Laplace, we can say that afterload is directly proportional to the left ventricular pressure during ejection and radius during ejection, and indirectly proportional to 2 times the left ventricular wall thickness. But for simplicity's sake, we say that the left ventricular wall stress during ejection is proportional to left ventricular pressure during ejection. And if we assume that left ventricular pressure during ejection is equal to aortic pressure during ejection, then we can say that left ventricular pressure during ejection is equal to what we commonly know as systolic blood pressure. Finally, factors that affect the left ventricular afterload include systemic vascular resistance, aortic pressure, and valve diseases such as aortic stenosis and mitral regurgitation.
And then we'll go back to the regular lecture. So your afterload is your force experienced by the ventricle after the contraction has started. Meaning, that's also a weird way to say it, the force now that my ventricle meets is my afterload. And so that's also the force that is needed to overcome opening the aortic valve and the ejection to begin. So the most common source of afterload is the aortic diastolic pressure that must be overcome to open up that valve and to begin the ejection. An aortic diastolic pressure increases. If that happens, like in high blood pressure, the myocardial cells must generate greater systolic pressure to initiate the ejection. So this burden reduces the speed of the valve opening and slows the velocity of the ejection once the valve is open. So then overall, the increased afterload therefore reduces my stroke volume, and at the same time increases the work of the heart. So if I have increased afterload, I have a high pressure sitting there that my ventricle needs to overcome to open up the aortic valve and to begin ejection. So if I have aortic stenosis, as an example, what's going to happen? I can't open up. I keep the valve narrowed, stenosed, and so now my stroke volume is going to decrease. but my heart muscle, my contractility has to work really hard to even get a decreased stroke volume out. Okay, so to put these together, we want to remember cardiac output is heart rate times stroke volume. Both components, heart rate and stroke volume, are under the control of our autonomic nervous system. Heart rate is decreased, which we call negative chronotropy, by our parasympathetic activity, and we get positive chronotropy or increased heart rate by our sympathetic activity. To determine our stroke volume, that is determined by our preload, our afterload, and our contractility. All three things influence stroke volume. When we talk about preload, we're talking about the Frank-Starling law of the heart. The greater filling leads to a greater stroke volume. When we talk about afterload, remember, afterload, it's the force the ventricle must overcome to achieve the ejection of the stroke volume. If you have a high afterload, that's going to decrease your stroke volume. Then our cardiac contractility is modulated by the let me start that sentence over. The cardiac contractility is modulated by the sympathetic nervous system in accordance with our body's needs, whether we are at rest or we are at exercise or demand. The sympathetic nervous system exerts a positive inotropic effect. Okay, but what it also does is accelerates ventricular relaxation, allowing for the better filling as the heart rate increases, so we also improve our cardiac output. Okay. Whew. We got through that kind of. Lots of information in the book. Really put together in osmosis. The next part that your book goes into is the cardiac cycle. We did watch that in the previous videos. The book now throws it in again here. Again, what they're trying to show us is that the heart functions by this cycle of both electrical and mechanical events. It alternates between ventricular contraction, which is our systole, and then the period of ventricular relaxation, which we call diastole. And when that happens, systole, diastole, that's a cardiac cycle. When we are at rest, our systole typically lasts a third of the cycle, and diastole lasts 2/3 of the cycle when we're talking total time. So that's a nice image then of the cardiac cycle. The book also has this view of the cardiac cycle, which I do think is nice to see in a different way. So this is showing the phases of the cardiac cycle and their corresponding events. Although many of the variables here can be only measured invasively, auscultation of heart sounds and the inspection of the jugular venous waves can be performed during a physical examination. So heart sounds are shown from the phonocardiogram data. S1 correlates with the closure of the AV valves. So when you hear S1, that's the closure of the mitral and the tricuspid valves, right? So systole, diastole. So when we hear S1, and you look up here, we're hearing the aortic valve, the AV valves, close. Okay. And S2 correlates with the closure of the ventricular outflow valves, which are our aortic and pulmonary valves. So we hear mitral, tricuspid, then we hear aortic, pulmonary. S3 can be heard during rapid ventricular filling and early diastole, where the atrial pressures vary during the cardiac cycle and can be deduced from the pulsations reflected back to the jugular vein from the right atrium. And we can see the abnormal jugular venous filling. What I think, though, here that's really nice to know is what are we seeing when we compare it to the previous cycle before, is our heart tones and where they are corresponding into our PQRS. So when you hear S1 and then you hear S2, we are in the middle of our cycle, right? So S1 should be close to the QRS happening, which is then the ventricular depolarization or squeeze during systole. And then diastole is where we would hear the S3. And it's kind of showing it that way through. One of the ways that you can also look at a cardiac cycle is through the pressure volume idea and these kind of loop volumes, if you will. So this one is showing the pressure volume loop. So the pressure volume loop describes changes in both our pressure and our volume as they're taking place during the cardiac cycle. So when we talk about end diastolic pressure and the volume relationship curve, what we're trying to say is how easy is it to fill the ventricle? And it's not that easy. These figures here, we can see that they are moving in a counterclockwise direction. At point A, okay, this is then the atrial pressure. Think about this. The atrial pressure now is exceeding that in the ventricle, which is what causes the mitral valve to open and permit the initial filling of the still relaxed ventricle. So A, we're seeing is the mitral valve open. Okay. At point B, the ventricle is fully relaxed and is filling as the atrium starts to contract. At point C is the onset of the ventricular contraction because the left ventricle's pressure exceeds that of the atrium, and so the mitral valve closes. At this point, then, the ventricular pressure rapidly builds, but the volume does not change. Right? So this was the volume of 0 up to like 150 milliliters. So then our mitral valve closes, and this is our end diastolic pressure volume relationship here. So this is the onset of the ventricular contraction when our left ventricular pressure has now exceeded that of the atrium, so the mitral valve is closing. At this point, our pressure builds rapidly, but the volume stays the same. So they call this the isovolumic contraction. Because at this point, the pressure has not exceeded the aortic pressure. At point D, then, the left ventricular pressure exceeds the aortic pressure. So we have squeezed hard enough that we are going to create enough pressure that we have popped open our aortic valve. So the aortic valve opens and we begin to eject the blood volume. So now we start to go backwards on blood volume. So we're pushing out. At this point, my ventricle is full. My volume is at its greatest, its pressure. I'm building the pressure. It pops open my AV valve. I'm starting to get rid of my volume, ejecting it into the arterial system. So you can see now my volume of the ventricle starts to move backwards. When we get to this part here at D, the pressure at point D corresponds to our diastolic blood pressure. So at this point, right, look, I'm getting up to, let's see, 100 and whatever this is here, like this would probably be 90. The peak ventricular aortic pressure then is noted at E, and this is where our systolic blood pressure is probably noted here. After the ventricular contraction is maximized, so it hits a peak, and then it starts to drop the pressure as we're still dropping the volume. So we're now looping back down this way. When the left ventricular pressure is lower than the aortic pressure, the aortic valve closes here at the F. The ventricular pressure then precipitously falls back to A. And at this point, we're at rest. I have very little volume and I have very little pressure in here. Because the aortic valve and the mitral valve at this point are still closed, the left ventricular volume cannot change. So now we call this the isovolumic relaxation until the pressure drops below that of the left atrium, which then reopens the mitral valve. So I'm going to make you guys record a video of yourselves speaking this out loud so I know you understand it. No, I'm just joking. I know some people think, when am I ever going to see a pressure volume loop again? You do see this in the ICU. You do see this in balloon pumps and some of the other things down the line. So you may very well see this again in your career. What I like about this, though, is that these pressure volume loops here help us really, what we're doing is we're really understanding the concepts of what is happening at the same time. Because this shows us that we're building pressure, we're changing the volume, all these things are occurring at the same time. So to be able to walk through this and describe this to yourselves is very good. Like, if you want to pause this now and say it out loud in your head, can I describe what this means and what I'm trying to say through that, right? What are we trying to do? The other parts on here that are important to know is that our end diastolic volume, which is our EDV, right? So EDV here, our end diastolic value. So at the volume, at the very end of rest, our end diastolic volume is corresponding to the total volume in the ventricle achieved during diastole. So at this point here is our end diastolic volume. And that's really important because think of that this way. That is the total volume in the ventricle achieved during the diastole phase. So that is the total volume I get after my complete balloon filling, right? So is my end diastolic pressure reflective of my preload? Right? Does that make sense? So that's an important thing to know because it's easy to determine the difference in the ventricular volume between the onset and termination of systole, which we can see at F. So this volume is the stroke volume, which is the volume of blood that's ejected during the single cardiac cycle. Okay. So let's say that one more time, make sure we're understanding what we're seeing here. The EDV is our end diastolic volume, and that is showing us the total volume in our ventricle during diastole. Okay. So at the end of diastole, our end diastolic volume, that volume is now our preload. That is the volume that came into the ventricle to stretch it as far as it was going to go with that maximum stretch, maximum fill. That is my preload. The other name for this then at this time is my stroke volume. So using this here, what you would say is that the difference between your ventricular volume between the onset and the end of systole. So when systole starts and when systole finishes is what we would see here, which is our stroke volume. A portion of, this is important to remember, I'm sure you guys know this, but let's refresh our brain. A portion of the left ventricular blood remains in the heart after each contraction. You don't actually squeeze that ventricle empty. The residual volume remains because the heart cannot completely empty during a single cycle. Interesting fact, the residual volume is normally about 40% of the end diastolic volume. So, a commonly used index of cardiac function is the ejection fraction. it is calculated as the stroke volume divided by our end diastolic volume, which is typically around 60%. Okay. So now you guys can explain to people much more clearly what your ejection fraction is, right? Oftentimes in layman's terms, we just say it's how much blood your heart can pump out with each cycle. It shows me how strong your heart is. When you have a weak heart muscle, your EF goes down. That's how I explain it to patients. That's the very simple layman's term. But what we're actually saying is, think of it this way, at the end of systole, so let's put it this way, at the end of diastole, right? Let's say I have 150 mLs of blood in there, okay? And I squeeze. So at the end of diastole, my end diastolic volume or my stroke volume, let's say it's 150 cc's, milliliters, okay? I have a good contractile squeeze, so my heart squeezes, but the blood doesn't empty at all. So even with a nice, strong, healthy heart, we should have about 40% of our end diastolic volume left over in that ventricle. So we should have about 40% of our stroke volume left in the ventricle. We have about 40% of our preload in our ventricle at the end of systole, which means that I ejected about 60% as the fraction of the blood volume I was able to eject out during systole. So when we say your ejection fraction, it is literally telling us that we know you're only going to get rid of a fraction of your blood each cardiac cycle. So you should get about 60% of your blood out during that cycle. So if my EF goes down, that is telling me that my pump is weaker, and then my cardiac output is going to be weaker. Because remember, your cardiac output is your heart rate times your stroke volume. So my stroke volume, that number is my end diastolic volume. And so whatever that number is, if I can only eject 30% instead of 60%, I have a significant decrease in the volume that I'm ejecting with each cardiac cycle. So reduced EF is saying that's a big deal. My heart is weak enough now that I'm not able to get my cardiac output to what it should be because I'm limited in my stroke volume because of something is impacting that ability of my heart to squeeze strong enough to get 60, 65, 70% out. That's a nice, strong, healthy heart. When you start dipping below 50, now we're definitely getting into what we would be indicative of like a heart failure, because now we are not able to keep up with our cardiac output. I'm jumping in here with some after video editing to add in the osmosis video for changes in pressure loop volume. So if you listened to that first part and heard me explain it, well, then I'm sure you'll probably think this is even better. So let's listen to osmosis here.
If you've already watched the first video on pressure volume loops, then you'll know that the pressure inside the left ventricle is on the y-axis, and then the volume of the left ventricle is on the x-axis. And each loop represents one cardiac cycle. So that's ventricular systole and diastole. It's basically just a heartbeat. The bottom right-hand corner of the graph is called the end diastolic point. And you guessed it, that's the point in the cardiac cycle when diastole is over. So at this point, the mitral valve is closed and the left ventricle is filled with the maximum amount of blood that can be inside it. And that amount is known as the end diastolic volume. After that, the left ventricle contracts, and that's the beginning of systole. When the ventricle contracts, it makes the pressure shoot up. But because the mitral and aortic valves are still closed, the left ventricular volume doesn't actually change. So this phase is called isovolumetric contraction, because iso means the same, and volumetric refers to the volume. Eventually, after the pressure's been getting higher and higher, it ends up being higher than the pressure inside the aorta, so that forces the aortic valve to pop open. and that's the start of the ejection phase. In the ejection phase, the blood is squirted out of the left ventricle into the aorta, and so as this happens, the volume in the left ventricle goes down. So the left ventricle continues to contract, and ventricular pressure keeps on getting higher and higher, but then it starts to fall a bit when the aortic pressure exceeds the pressure in the left ventricle. At this point, the aortic valve shuts, and this is the end of systole, which is really imaginatively named end systolic point. So to continue our theme of really imaginative names, the pressure in the left ventricle at this point is called the end systolic pressure, and the volume in the left ventricle at this point is called the end systolic volume. Now I know what you're thinking, that's all too exciting, but if you think that's exciting, then get this. So the difference between the end diastolic volume and the end systolic volume is called the stroke volume. After all of this, the left ventricular muscle starts to relax, and so the left ventricular pressure starts to fall. But the aortic and mitral valves are still shut, so the volume remains the same. So you remember how when the ventricle was contracting, but the volume remained the same, we called that isovolumetric contraction? Well, now it's isovolumetric relaxation. After a while, the ventricular pressure drops so low that it's lower than the atrial pressure, so that causes the mitral valve to open, and then blood rushes from the left atrium into the left ventricle. As the ventricle fills up with blood, the volume rises back to what it was at the end diastolic point, but the pressure only increases a little bit. This relaxation phase goes on until the mitral valve shuts, and then the loop can start all over again. All of this stuff happens during just one heartbeat, and with every heartbeat, or stroke, the heart is doing work, and that is called stroke work, and it's proportional to the area inside the loop. So in other words, the bigger the loop and the more area inside of it, the more stroke work is being done. Sometimes this is shown to look like a box, which is basically just drawn over the top of the pressure volume loop, and it looks like this. The vertical dimension of the box is the distance from the x-axis to the end systolic pressure, and the horizontal dimension is the stroke volume. So in terms of stroke work, it would be the area inside the box. And the box isn't exactly the same as the loop, but it's a good approximation. Okay, so now we know what a normal pressure volume loop looks like, but let's go ahead and change some stuff up and see what it looks like now. First of all, let's increase the preload by adding more blood to the left ventricle during diastole. So that means that during diastole, this bottom line goes further, and that increases the end diastolic volume. And then, because of the Frank-Starling relationship, there's a nice big strong contraction. And the isovolumetric contraction phase doesn't look any different, but once the blood gets ejected, it becomes pretty clear that there's going to be a larger than normal stroke volume. And then the end systolic pressure and volume end up being about the same as what they were before. So overall, an increased preload leads to a larger pressure volume loop, and that means increased stroke work. Okay, now let's try out another change. Let's say we increase the afterload by increasing the blood pressure in the entire arterial system, including the aorta itself. That means that during isovolumetric contraction, the pressure in the left ventricle has to get higher than it was before because it needs to exceed the aortic pressure, which is higher. That's the only way we're going to get the aortic valve to open. During the ejection phase, relatively high pressured blood leaves the ventricle until the aortic pressure is higher than the ventricle pressure. And since there's elevated blood pressure in the aorta, the end systolic pressure ends up being higher as well, and that means that there's a relatively small stroke volume. It also means that there's more blood left in the ventricle at the end of systole. In this situation, there's a bit of a trade-off, because there's a smaller stroke volume, but there's higher pressure. So it means that the stroke work works out about the same, remaining relatively stable. So we've tried out two changes. Let's go for one last change and up that contractility by giving a medication that makes the heart contract more forcefully. Increased contractility means that during the ejection phase, the blood is under higher pressure, and so the ejection phase goes on for much longer. The ejection phase comes to an end when the left ventricular pressure is the same as the aortic pressure. So they have the same end systolic pressure, but now that point occurs with a much smaller left ventricular volume. So in this situation of increased contractility, there's now a big increase in stroke volume, so there's a larger stroke work. And even though the end systolic pressure is unchanged, because the blood is under higher pressure, it means that the size of the pressure volume loop is bigger. Okay, so that was quite a lot of information to take in, but let's just quickly go over the main points. So pressure volume loops can be used to visualize the effects of a changing preload, afterload, and contractility. An increase in preload and contractility increases the size of the pressure volume loop, and therefore it increases the stroke work. An increased afterload, though, increases the pressure, but decreases the stroke volume, and so that means that stroke work remains relatively stable.
And that's what we just talked about through there. I like the other one better. I think it's easier to understand what we're saying when we can see the previous imaging. Let's go back up to that one for a second, okay? So our diastolic filling generates a pressure within that relaxed ventricle, right? So that's Starling's law. As that volume is coming in, that balloon is going to be stretching to a certain peak pressure. It can't go any further than that. We can stretch those fibers as far as we can, okay? The magnitude of the pressure that's going to be created during this filling of the balloon depends on the volume of filling. So if you have more volume coming in, you're going to be generating greater pressure. So how much we can fill during diastole is dependent upon our preload, but it also is dependent upon whether or not the ventricle wall is able to do its job. If you have a stiff ventricular wall of the ventricle is stiff, now you have diastolic dysfunction, so you cannot stretch the balloon the way that you should. So that relationship is depicted in this by the ED-PVR line. So an increased diastolic filling increases the ventricular pressure, contributing to the stretch of the ventricle. That promotes improved stroke volume, according to the Frank-Starling relationship. But the ability of the ventricle to eject a normal stroke volume is limited by the ES-PVR line, which represents the segment of the overall length of tension the Starling curve has of that ventricle. The pressure volume loop can also be used to determine the cardiac work, which is the ability of the heart to eject blood against the aortic pressure. The area within the pressure volume loop correlates with cardiac work and the energy demands of the heart. So next we go into the idea of what happens when we increase preload. So now we're talking about a pressure volume loop to a certain degree here with preload changing. So what we're seeing here is that because of the Frank-Starling mechanism, increased preload increases our stroke volume, because the more I stretch and fill, the more I'm going to be able to eject. But an increased preload also increases cardiac work and metabolic demand. In contrast, the increase in the peak systolic pressure is relatively conservative. So this is showing us that the widening of the stroke volume suggests that increased preload will also increase cardiac work and metabolic demand. So now when you look at that, though, in terms of afterload, the effects of changes in our afterload can also be depicted with our pressure volume loop. Remember, as the aortic pressure increases, the stroke volume is going to decrease. So the harder it is to get the aortic to do what I need it to do, the aorta, I'm not going to be able to get as much volume out. The cross-sectional areas within the loops are minimally affected by an increased afterload. But this shows how cardiac work is unaffected by increased afterload, but it reduces cardiac output. So a vasodilator, which will reduce afterload, will increase cardiac output with minimal effect on the cardiac work. That is a lot of words, a lot of things to say there, but I want to really think through that again, because this becomes really important when we're treating heart failure. Okay. So because the aorta or the afterload, if it's high, then our stroke volume decreases. Okay. So if I were to give somebody a vasodilator, so my aorta, think now that pressure that's created my total peripheral resistance, and in order to overcome that total peripheral resistance in the arterial system, I have to generate enough pressure to open up the aortic valve and to overcome that. So if I'm really constricted and tight and I've created a very narrow opening, I'm not going to be able to get as much stroke volume through that narrowness of that plumbing, and my heart's going to have to work really hard, right? If I open that plumbing and I vasodilate, so I give a drug that's a vasodilator, I'm reducing the pressure, I'm reducing the afterload. It's going to increase my cardiac output, but it's not going to ask my heart to work any harder. It just relaxes the vascular system, and this becomes important down the line. So this one here on this is showing us that as afterload increases, arterial pressure increases, right? The ventricle has to work harder to overcome high diastolic pressure to open the aortic valve, and it must continue to have even stronger contraction to eject the stroke volume against a rapidly rising systolic pressure. So those factors result in a decreased stroke volume, but you're still working the cardiac work the same. This becomes apparent as we get further down and talking about things with stroke volume and vasodilators and all of those things. So when we're talking again about this whole time, it's been the heart as a pump and how it functions. We're going to talk it through one more time to wrap it up. Okay. The cardiac cycle is a coordinated sequence of electrical and mechanical events responsible for generating the rhythmic contractions of the heart during systole and relaxation of the heart for filling during diastole. Our cardiac output is our stroke volume times our heart rate, and those are going to vary depending on the body's oxygen requirements, whether we're at rest or with exercise. Our heart rate is under our autonomic control. Our stroke volume depends on extrinsic control with the sympathetic nervous system because it will act as a positive inotrope. The factors that affect our stroke volume would be preload, afterload, and contractility. Relaxation of the ventricle is regulated by our sympathetic nervous system as well. Okay. Talking about the actual blood flow to the heart itself, to our cardiac muscle itself. Let's review this. In normal cardiac function, the delivery of oxygen typically matches myocardial oxygen demands. The heart has very high oxygen extraction of 70 to 75% at a resting heart rate and contractility. So, if you have an increased oxygen demand because we're exerting ourselves or we're exercising, that must be met by an increase in coronary blood flow as well. So in other words, I like to think of this as the heart muscle is very greedy for oxygen. It needs to be well oxygenated. So if all of a sudden we need to work harder and the demand on the myocardium significantly increases, we have to make sure we increase coronary blood flow, or we're not going to be able to meet the demand of the body as well. If the oxygen needs of our myocardium are not met, that's when we're going to get ischemia, right? And have a heart attack. So, with any issue of oxygen in the body, so our heart has to work harder, then our heart needs to be oxygenated better itself as well. Okay. So we're talking now about cardiac oxygen supply and demand, okay? Oxygen delivery requires adequate pulmonary function right? Because we need to oxygenate the blood and get rid of the carbon dioxide. That's an important component of this as well. And we have to have adequate blood flow to the coronary arteries. So since the coronary oxygen extraction rate is so high, the delivery of oxygen to the coronary tissues must be carefully regulated. Coronary blood flow is pulsatile, but in contrast to our other organs, it has a peak flow during diastole. So that's very unique. I like to think of this as though at the time when the heart is stretching and pushing, that is also creating the time for us then to push our blood into our own muscle and oxygenate the heart itself. Kind of an interesting idea, but I like it. Helps me figure that out that way. It's actually something that the book shows us. Actually, I was trying to find that. This is figure 10.1 or 10.31. And this is showing us the coronary blood flow in systole and diastole from both the right coronary artery and the left coronary artery. And so we'll talk about that again too here. Because the myocardial blood flow varies, right? The total blood flow through the coronary vessels is maximal during diastole. The higher blood flow through the left ventricle is due to its greater mass and higher oxygen consumption than on the right ventricle. So our right coronary artery, you can see blood flow is going to be less than our left coronary artery, right? And that's because our left coronary artery feeds the left ventricle, and the left ventricle is a lot bigger tissue and it demands a lot more oxygen to be delivered to it. So it is going to get more blood flow delivered to it than the right side of the heart, which is the weaker, quote unquote, side of the heart. Okay. During systole, the cardiac muscle contracts and compresses the coronary vasculature, increasing its local resistance and limiting blood flow. But at the onset of diastole, the coronary blood flow then increases depending on the aortic pressure. As the aortic pressure drops during diastole, right, the ventricles are relaxing and they are relieving the coronary vessels from compression. And it's that drop in that resistance that allows the local coronary blood flow to all of a sudden surge and supply the heart. This diastolic surge is also reflected in the right branch, but it's attenuated due to the relatively smaller and thinner right ventricular wall. So overall, our coronary blood flow is maximal during diastole, but reduced during systole. So the duration of diastole affects our total myocardial blood flow, right? That makes sense because the time that we perfuse our own heart tissue is during diastole. So however long the duration of diastole is going to affect how well we can actually supply oxygen and blood flow to the heart muscle itself. Diastole during a resting heart rate of 70 beats. So if we are sitting at rest at 70 beats a minute, and it's typically 2/3 of that cardiac cycle, the heart is only actively engaged in contraction about 1/3 of that time, with recovery and maximal cardiac perfusion during the remainder. But as heart rate then increases, our duration of rest shortens, and while the duration of systole remains relatively constant. And it is that shortening of our diastole, our rest time, that shortening is paralleled by a shortened period then of coronary blood flow. This reduces the blood and oxygen supply at the same exact time as we're increasing systole. So at the same exact time we're asking that heart to work even harder and faster is when we also at the same time stop supplying it with the same amount of blood and oxygen, right? So the shortened diastole time when our heartbeat it goes faster, also shortens the period of time that we have to get our own blood flow to the myocardium. So you are at greater vulnerability to ischemia or problems when your heart rate increases, especially if patients then have compromised coronary arteries due to arterial sclerosis. So that's why sometimes people that get very symptomatic with exertion is that even at narrowed blockages, because the narrowed blocking when our heart rate goes faster, that little bit of narrowing is enough to make a big difference because we don't have the same amount of time to deliver blood supply and oxygen to the coronary arteries themselves. Okay. The other part to point out here is that the majority of the flow to the left ventricle is what we're talking about during this time, because the right ventricle does get it between both diastole and systole because it doesn't need as much in the way that the compression works, and that smaller, thinner ventricle makes things different. Coronary vessels travel epicardially, giving rise to branches that feed the thickness of the myocardium. We'll see that again here in a minute. Our rich capillary networks surround our muscle cells, so we can have collateral connections between the vessels that can provide flow around the blocked regions. The high oxygen extraction of 70 to 75% of oxygen is removed due to high rate of aerobic metabolism. The mitochondria make up about 30% of the myocardial cell volume. They need a lot of oxygen to work. The other concept to understand is that our coronary blood flow is also under autoregulation. So this intrinsic property of our heart to adjust our coronary vascular resistance to maintain coronary blood flow despite changes in the pressure, right? So in addition, local endothelial and vascular factors will contribute to our regulation of our blood flow. A lot of words for saying, just like we covered in chapter 9, we have intrinsic properties of our heart to try to control our coronary vascular resistance as well. This one here is showing us, again, the factors that reduce coronary blood flow. It's another way to look at it, as we've talked about already. The increased heart rate means less time in diastole, so less time to fill the coronary arteries. Our increased ventricular systolic pressure creates pressure within the wall, and that compresses our coronary vessels. If we have atherosclerosis, we will get turbulence in the coronary arteries, but we also eventually will have narrowing of the lumen. Microvascular disease, decreased flow-dependent dilation of small arteries and large arterioles. And then vasospasm due to sympathetic activity and other vasoconstrictors would also reduce our coronary blood flow. Anything that's going to spasm and shrink down the size of that coronary artery. Factors that are going to increase our heart's oxygen demand these make sense when we think about them, right? If we have an increased heart rate, if we're asking the heart to beat stronger with an increased contractility, if we have sympathetic stimulation, that means our heart rate and our contractility went up, so we would need more heart oxygen. When we exercise, we need more heart oxygen. Now listen to this one and think about this a second. When we have increased afterload, we have to have increased contractility. And we already know that increased contractility causes an increase in our heart oxygen demand. The things that typically we think of when we think of an increased afterload are going to be hypertension, chronic hypertension, and aortic stenosis. What happens then is that over time, as that heart has to work harder, and the coronary tissue demands more oxygen, our body tries to compensate by developing hypertrophy. So if you have left ventricular hypertrophy, that is an adaptation that happens as it increased to chronic afterload increased. Okay. This is a picture of our coronary blood supply, which I think is nicely shown here for us. Those of us that have worked in the cath lab before, we know this probably well. Maybe those of us in ICUs that read a lot of 12 leads would know this well, or work in cardiovascular units might know this. Maybe some of you need a good refreshing of this, so let's talk this through. The left and right coronary arteries arise from our proximal aorta, behind the cusps of the aortic valve, and they travel in the epicardial layer, giving rise to branches that penetrate into the myocardium itself. Okay, so we have that feed into the tissue. We have the left coronary artery, okay, that bifurcates and becomes down here to cover the left ventricle. This part here is the left circumflex. Then they have the left marginals, and they come down into the LAD, which is the main one here, right? And that is the left anterior descending artery. They also call it the intraventricular artery because it can help supply blood to the right ventricle as well. Then we have the diagonals coming off of the LAD. Then from this main coronary artery here, then we have the right coronary artery that comes down here. From the right coronary artery, we get the posterior descending artery, or the PDA, that's feeding the back of the right ventricle. Then we have the right marginal artery as well. So that's a nice picture for us to review the coronary arteries themselves. And they travel along the epicardium so they can feed into the myocardium. And my things around there. We talked about this already. All right, I'm going to pause here to make this part 2, video 1, and we'll see you again in video 2.